Hello, thanks for joining us. This is Writing Extension Modules to be Interruptible. Please welcome Zack Weinberg.
Hello, everyone. I'm Zack Weinberg, and I'm here to talk about making extension modules interruptible. Why that's a thing you have to do by hand and not just a thing that happens, and how to do it, which is harder than it might look, and how to do it efficiently, which is easy but requires measurement to make sure you got it right. And finally, how we might change things to make this at least somewhat easier. So first, let me introduce the problem. If you've used Python for interactive number crunching, there's this good chance you've tripped over this bug. You set up a long calculation as a, whoops, that's the wrong button. Sorry, this is not my usual clicker. Here's an example of a calculation that you might do with NumPy that takes a long time. It's just a demonstration, so all it's doing is generating a big vector of random numbers. You run it, and you realize, wait, I forgot to assign the result to a variable, so you hit Control-C, and now you wait, and you wait, and you wait. And eventually the prompt does come back. On the computer I tested this on, it was about a 3-second delay. If you're doing something bigger than just a bunch of random number generation, it can be minutes. And of course, all that CPU time is just wasted, thrown away. What went wrong? Why is this? Well, it's a bug in NumPy. It didn't call this particular CAPI function PyAir check signals, ever. I'm not here to pick on NumPy. A lot of my examples are NumPy, but huge numbers of extensions have this exact same problem. It's a really easy thing to do without meaning to, without even realizing that there's something you forgot to do if you're writing a compiled code extension for CPython. But it is a bug. It's something that I hope we can all pull together and get fixed. And the long version, unfortunately, is the rest of this talk. Why there's no way to avoid needing to change all the extensions to do this thing that they're not doing. Why they're not doing it now, when it's been a requirement, as far as I can tell, since before CPython 2.0. And how can we make it easier for extensions to do this? Because it's not as easy as it might look. And before we get to the meat of this talk, I want to say up front, there isn't an easy fix. This is something that every single author of a compiled code extension is going to have to change by hand. There's no thing we can change in core CPython, just make the problem go away. And there's no workaround. If you're just programming in Python, sorry, but we got to have the people, we got to do the legwork. And the rest of this talk is about what those changes that need to be made and why. And this necessarily goes into fairly low-level details of the CPython interpreter and what happens at a low level when you hit Control-C. And I'm going to do my best to introduce these things gently, but I only have half an hour, so I'm sorry, but I'm going to have to assume a bunch of background. You're going to get more out of this talk if you have ever written a compiled code extension before. You're going to get more out of it if you've written code in a compiled language at all. If you know the essence of how a bytecode interpreter works, not necessarily CPython itself. And incidentally, if you already understand the dangers of Unix signal handling, there's a big chunk of this that's not news to you. And last footnote before I really get into it, I'm going to show you a bunch of measurements. I'm going to show you a bunch of code. It was all done and tested using Python 3.12. I haven't had a chance to try anything newer. And in particular, that means if you're super pumped about the free threading project, well, I am too, but I'm going to say global interpreter lock a lot. And the thing is, I don't think the free threading actually changes the rules for how you have to call these CIP API functions that I'm going to talk about. So just mentally sub in attached thread state whenever I say global interpreter lock, and we'll be fine. And come find me afterward if you have notes. Right. Why does the bug exist? Some interpreted languages do not have this bug. If you run a big long shell pipeline with a slow operation like a sort in the middle, and you hit Control-C on that, boom, you get the prompt back instantly. And the sort utility isn't doing anything special with Control-C. Maybe it's cleaning up some temporary files, but that's it. Why isn't this a problem for shell when it is a problem for Python and probably also other, I didn't test this, but other programming languages like Python, such as Perl and Ruby? I bet they have the same problem. And one answer is Python is being fancier. Python lets you catch keyboard interrupt if you really want to. The docs say don't, but it's possible. Shell scripts have trap, but trap does not let you keep going. Either you run some code and then you go back to what you were doing, which is very different, or you exit out of the whole shell script. And the other answer is shell scripts are getting more help from the operating system. I'll come back to that at the very end of this talk. Just keep it in your mind until then. Shell script don't have, and they get more help from the kernel. That's why. Okay. To understand why CPython needs compiled code extensions to help it out when somebody hits Control-C on it, we need to understand what Control-C actually does. It's not something Python invented. It's at least a decade older, and part of how it works is built into the Unix kernel. So we're playing by old rules, rules designed and implemented by 1970s era system programmers. Keep that in mind. And by the way, a footnote, this is not how it works on Windows. I don't understand what Windows actually does when you hit Control-C. I just know it's different, but it's not different in a way that matters. The thing that Python extension authors need to do is the same, regardless of if we're on Windows or not Windows. So it starts out like any other keystroke. As far as your keyboard controller is concerned, it's just the Control-C and the C key, and there's this vast array of pre-processing stages that we're just going to skip, like SSH. If you've got an SSH in the middle, it just passes the Control-C along. But right before it gets to the Python interpreter, there's this thing called the terminal line discipline inside the kernel, and it takes the Control-C out of the normal input stream and it turns it into a thing called a signal. And the name of the signal is SIGINT, int for interrupt. And that gets delivered to the Python interpreter instead of the normal input, and the interpreter reacts to the signal by raising keyboard interrupt. Now these two words here, delivered and reacts, these are crucial. The delay is in between delivery and reaction. I'm going to go into more detail about what delivered means in a moment, but the gist is at the moment of the delivery, a special function inside CPython, it's called signal handler, not exciting, but it only ever called when a signal comes in, and all it does is set a flag. Nothing more happens until CPython gets back to the main interpreter loop. And the main interpreter loop checks the flag as part of some bytecodes. If you look through bytecodes.c, it's the ones with the check periodic op in them. And they detect the flag that's set, and then they raise keyboard interrupt. And this is also what PyAir check signals does. It does the same thing that the periodic op does. It checks the flag, and if the flag is set, it raises a keyboard interrupt. So why can't the special signal handler function just raise keyboard interrupt itself at the moment of delivery? Well, now to understand this, we have to look at what actually happens when a signal is delivered. So here's that random number generator function again, and I'm going to run it again and interrupt it again, but in advance, I hooked up CPython to the C-level debugger, GDB, which has intercepted the signal before CPython got to see it, told us we are in the middle of executing something called random standard uniform fill, and what would I like to do about it? Now, just a note, if you try this yourself, you're going to see a lot more clutter. GDB is a very talkative program. I cut out a bunch of uninteresting stuff from these slides. Now, this is the function on top of the C-level call stack, random standard uniform fill. That sounds like part of NumPy's code for generating a bunch of random numbers all at once, right? So that makes sense. That's the slow thing that most likely to be interrupted. Let's let the signal go through to CPython now with the signal command to GDB. And in advance, I set a breakpoint on the special signal handler function. So now we're executing the special signal handler function. As far as the kernel is concerned, the signal has been delivered. It's done. Hands off. Everything else, everything from this point on is up to CPython. And as I said, CPython is just going to set a flag. Why? Well, I can't fit the whole debugger transcript on the slide, so let's scroll up. And we're still right where we are at the end of the previous slide. Stopped in the breakpoint. Let's look at the stack trace. Now, incidentally, GDB prints stack traces upside down from the way Python does it. So the innermost frame is on the top. Here's signal handler. And above that, let's de-emphasize some of the clutter. Right above signal handler is this weird signal handler called special stack frame. And oh, it's random standard uniform fill again. And above this is more stuff that looks like more of NumPy's random numbers module. So, how did we get from random standard uniform fill to signal handler when there certainly isn't a function call that would do that? And what's going to happen when we return from signal handler? Okay. Signal delivery was invented by those operating system programmers from the 1970s. They thought in assembly language. They designed signals to be like hardware interrupts. So what happened was it comes some completely arbitrary point between two machine instructions in the middle of random standard uniform fill. The operating system kernel has taken control away from CPython. It's called preemption. Messed with the saved register state, written fake stack frames to the machine stack, and then restarted execution at the beginning of the signal handler function. When the signal handler is done, those fake stack frames are going to make the CPU run a little bit of private code from the C library that cleans up. That's what that mysterious signal handler called frame was about. And then it'll go right back to exactly where it was in random standard uniform fill, which will go on with whatever it was doing, obliviously. And this is why we have to just set a flag. It's not safe to do anything else. We do not know what was happening when we were interrupted. When I ran the same test on a pure Python version of the same operation, when I hit Control-C, it was almost always allocating memory when the signal handler run. You can't mess with that. So CPython doesn't have a choice, is what I'm getting at here. We don't know what was going on when we were interrupted to run the signal handler. It's just like hardware interrupts. You want to get out of the interrupt handler as fast as possible, postpone the real work to a safe point. And so this is why we have this delay, because here we are again. The code that checks the flag in CPython proper executes all the time, because CPython proper spends all its time, practically speaking, in the main interpreter loop, which you never go very long before you get to a bytecode op that checks the flag, because, for instance, all the branches check the flag. But if we are executing code in a compiled module, the only way checks get into a compiled module is if the author of the extension put them there by calling pyare check signals. So that's the root cause. All the extensions, they need to be calling pyare check signals, and they're not. So why not? Why is this such a common bug? Why is everyone I've told about my talk going, oh gosh, I've totally tripped over that? I see three reasons, and I'd like to begin with the most basic one, which is I bet a lot of people who have written compiled code extensions in good faith, intending to get all the little details right, they still didn't know they needed to be doing this. And here's why. Here's the documentation for pyare check signals. Wow, that's a big wall of text. Let me highlight the critical sentence. This function can be called by long-running code that wants to be interruptible. That doesn't sound nearly as important as it actually is. If I'd written this documentation, I might have written something like, long-running code needs to call this function periodically in order for the interpreter to be responsive to user interrupts, or something like that. And I'd have made it the first sentence, not the second to last one. Not to mention, before you can get to this wall of text and read it and realize the implications, you need to find it. This is the only mention of this problem in the whole of the reference manual, buried in the signal handling section of the exception handling chapter of the C API reference manual. The extending and embedding guide does not mention this issue at all. And by the way, there's another sentence in here that's really important, really easy to miss. This one. If the signal module is supported, this can invoke a handler written in Python. Think about that for a moment. PyAir check signals might run arbitrary Python before returning to you. So that means you got to be careful about where and when you call it. And so that brings me to issue number 2. Even if you do know you ought to be doing this, well, you might need to really carefully refactor your code to make safe places to call it and to propagate its -1 return value that says, like any other C API function that says, hey, I set the error indicator. We are now throwing an exception. Stop what you're doing. Propagate failure all the way back up. That's, like, remember, C does not have exceptions. Fancier compiled code languages have a better way of doing this, but man, there's a lot of C out there still, and we gotta fix all of it. And sometimes that means changing layer after layer after layer of codes just so that this thing that formerly could never fail can now fail in the middle of its operation. So let's go through a simple example, really the simplest possible example of what change you might have to make. Here's random standard uniform fill. Again, somewhat simplified from the real code. And it's just a for loop. If you haven't seen C before, this is just for in C is just like for in Python, except you have to spell out the math. And all it's doing is assigning each element of an array in term to the next double precision floating point value from the random number generator. And so in principle, all we need to do is add a call to PyAir check signals inside the loop. It's got to be inside the loop or it won't work, right? Once that loop is done, the whole operation is done, and we've blown our chance to react sooner than before we were done. But notice I had to change the return type of the function. It's no longer void. It can now fail. And by making this function interruptible, I introduced a new bug. So here's I've just slid it over to the left. But remember, PyAir check signals can run arbitrary Python code. It's got to be safe to run arbitrary Python code. For example, you better hold the global interpreter lock. NumPy is really diligent about releasing the global interpreter lock when it's going to run a long, slow operation like this one. So we can't just call PyAir check signals. We need to reclaim the global interpreter lock, which you do like this, with these even more obscure C API functions called pygil state ensure and release, buried even deeper in the manual. And there's a whole PEP about how they're dangerous, PEP 788. But the thing is, they're the only functions I can find in the whole C API that actually do the specific thing we need here, which is take back the lock, but only if we've released it. Don't deadlock if you're being called by code that hasn't released the GIL. And also, don't make me pass down a PyThread state argument. This is bad, right? If you have a better idea, I'd love to talk to you after the talk. But this does work, as long as long list of caveats. And it's probably good enough for most extensions. Although, like, look at all this code I just shoved into the middle of this tight innermost loop. Code that does expensive things like taking and releasing mutex locks. So the most straightforward fix, the one I just showed you, makes all your innermost hot loops slower. Nobody likes that, right? But how expensive is it really? So I'm going to get out my lab coat and measure it. But I didn't measure the NumPy generate a zillion random numbers thing that I just showed you. I decided I should find a more interesting example. I don't expect you to read all the code on this slide. This is the core of the simplest fast Fourier transform implementation that I could find. Originally written by a fellow named Mark Borgerding. Are you here today by any chance, Mark Borgerding? Ah, that's too bad. Well, I'd like to thank him for writing an FFT implementation that I could actually make sense of. So what I want you to see about this is, first off, there's a recursive call in the middle of this brown block, which there's actually a loop that does a bunch of recursive calls. The base case is right above it, and down below, and both of these are making linear passes over the whole input array. And down here at the bottom, we have these B-fly for butterfly. This is just a standard FFT thing, also making linear passes over the input array. So we're over and over and over again, we're scanning the input array, and each of these scans takes only a few microseconds, so that's fine. We don't need to put a PyR check signals call inside any of these innermost loops, because a few microseconds of delay responding to a human action is negligible. So I'm like, okay, let's grab the GIL again, call PyR check signals, drop it again, go on. Let's put them here and here, where I've drawn these lines, after each scan. I figure that's probably going to be good enough. I figure this is this is a realistic version of the changes we'll actually need to make, although it does not work for just fill an array with random numbers. That's, and when you're measuring, you always want to measure the unchanged code first, right? So this is the cost of just the fast Fourier transform. We hold the GIL for the whole operation, and we don't do any signal checks. Incidentally, all the benchmarks are single-threaded, which means the global interpreter lock is never contended, which means this is the best case, okay? Nice linear relationship between FFT and execution time like you'd expect, or actually it's log linear because both axes are logarithmic, but that's not super important. And we add no measurable additional overhead by releasing the interpreter lock once at the beginning of the operation and taking it back again at the end, which is what you'd expect. If we don't release the global interpreter lock, there is a small but measurable cost to enabling signal checks. And just like we're single-threaded, we're not actually sending any signals in this benchmark. We are measuring the cost of having the checks in the code when they don't have anything to do, which is the normal case, right? This is where we care about the end-to-end throughput performance. But if we do release the global interpreter lock, suddenly the signal checks are a lot more expensive. Now, it's not easy to see by eye how expensive this vertical difference is, so I divided out the problem size, and this is what we get. And there's still an effect of the problem size due to the recursive structure of the fast Fourier transform, but what you should see here is this strip on top, the difference between these two strips is the difference of doing the checks if you held the global interpreter lock for the whole operation. And down below, it's the difference in time costs per sample if you do release the global interpreter lock. And wow, that's a big difference. That's like 3 to 4 times slower. So the obvious thing, what can we do about this? What's the easy, simple way to make this problem go away? How about we look at the clock? We don't check every time we hit one of those magenta markers on the previous slide, 2 slides ago. Every time we hit one of those markers, we ask the operators, how long has it been since the last time I called PyR check signals? If it's been more than a millisecond, which is getting up into human noticeable latencies, then we call PyR checks. Otherwise, we don't do anything. We don't even retake the interpreter lock. And that's going to be plenty good enough in terms of human responsiveness, but it really cuts down on the overhead. And notice that the overhead with and without the global interpreter lock is about the same. It's still enough overhead that you might be a little nervous about it. So there's another cheap, easy fix, which is if the operating system gives you a coarse monotonic clock, use that. Same deal, but like I'm just telling the OS I don't need nanosecond accuracy on my time here, and now we're like still measurable overhead, but overhead comparable to just the cost of adding the checks in the first place. Longer intervals between checks, by the way, do not help. A millisecond is awful short, but it's an enormous time to the CPU. The lion's share of the remaining overhead is the overhead of looking at the clock. We can't make that any smaller by increasing the interval. We're still looking at the clock every single time. Right, so recap. CPython interpreter cannot raise keyboard interrupt directly from its C-level signal handler. It has to go back to the main loop first. Do that promptly when the signal interrupted a compiled code extension requires cooperation from that extension. Many extensions don't do this. We've just seen why. It's not well advertised. It requires finicky code changes, and if you're not careful about it, it requires going to hit you with substantial runtime changes. So, great. Extension authors, what are we going to do about this? Well, short-term recommendation. Here's the code for looking at the clock, and I don't have time to explain it, but you can grab the full code from the link at the bottom of the slide, just copy and paste it into your extension, call this function, check signals often enough at appropriate moment. You still have to figure out where to do that and how to propagate the failure back up. But I've taken care of looking at the clock and being GIL-safe for you. It's only been tested on Linux and NetBSD, but given what it does, I'm pretty sure that's enough portability checking. 3-clause BSD, if you don't like 3-clause BSD, talk to my boss. Okay, so that's one piece of the problem, but there's still these other pieces of the problem. How can we make this better in other ways? I have some ideas. I'm going to tell them to you now in ascending order of zaniness. First off, let's improve that core documentation. Let's tell people they need to do this. Let's tell people how to do it safely and efficiently. I think we could be a whole new section in the extending and embedding guide. Not a zany idea. We should do this. I already filed the GitHub issue to say we should do this. Another thing that comes to mind is PyR check signals only actually needs the global interpreter lock if it has work to do. In order to check the flag, that is an atomic machine instruction. One atomic machine instruction. Don't need to take the lock. So what if we make PyR check signals pick up the lock for us only if it needs it? Then we don't need to be looking at the clock anymore because PyR check signals is now cheap if it has nothing to do. There's still like fine details, but I don't think this is a zany idea either, and I've actually already written the patch. So if you want to help me get it reviewed, that would be lovely. But we're still having to write the checks by hand. How can we make some tools help us? Well, awful lot of NumPy is actually written in Cython. This is more like the real actual in Cython, in NumPy code for this fill function we've been talking about. We could make the Cython Python to C compiler stick in these calls for us and take care of the error propagation for us. Maybe a little zany. I think this is doable. I've never actually looked at the guts of Cython. There's probably at least a few nasty gotchas lurking, but let's see if we can make it happen. In a similar vein, if you're working in a compiled language other than C, you have more tools available to you, such as Pyo3, which is the FFI from Python to Rust library, can do a thing called asynchronous functions that are cancelable. So maybe we can make Pyo3 map Control-C to asynchronous cancellation. This is completely hypothetical code of what that might look like. I don't know. I think this is, again, I think this is doable, but it's probably getting a little tricky. But still probably worth trying. And the last and zaniest idea. Remember I said the shell doesn't have this problem? The reason the shell doesn't have this problem is subprocesses. You hit Control-C on sort. Sort probably does not have a signal handler. The kernel just kills it. And the shell gets control back immediately. So what if we restructured the CPython virtual machine to work that way? Here be dragons. I don't know how hard this is. I think it's a non-trivial research project, but it's the only idea I've got that lets us not have to add PyAirCheck signals function calls to every compiled code extension on PyPI. And I'm out of time, so I was hoping to hear your ideas, but if you have them, come talk to me afterward.
Perfect. So thank you very much, everybody. Thank you. Great talk. If you do have questions, please do feel free to hang out. And do you have a place where you will be?
I don't have any plans for the rest of the afternoon.
Perfect. So just grab him on the corridors. Thank you very much for coming. And the next session is in 15 minutes. Thank you.